Okay. Now see, the idea is that we should have some basic initialization. Like we cannot start from very random representation of 3D Gaussians. So before running the optimization pipeline, we have to initialize the 3D Gaussians, the millions of 3D Gaussians, we have to initialize it. So that is what it is. And for initialization, we will be using structure from motion technique, SfM, structure from motion technique. But now one very important question, why initialization matters? What's the need for initialization? Because we know that, okay, we can start with random Gaussians, random 3D Gaussians. And at every step, like we will be computing the loss, updating the parameters, and we'll keep on doing it until the rendered image is very close to the real image. So why we are concerned about initialization? So the idea is that like one very important observation, like if we train from scratch, training from scratch with random Gaussians, it usually fails. And why it fails? Because see, in random Gaussians, if we start with random Gaussians, the scene, the 3D scene they are representing, it does not have any spatial structure, no spatial structure. Because of that, gradients will become meaningless. Rendering initially produces noise, and optimization gets stuck in local minima, or we call it bad minima. So without initialization, it might happen that we are not able to optimize it. Like if we are updating the weight, that the parameters also to minimize the loss, we might stay stuck in local minima, bad minima. And because of that, gradients will start becoming meaningless. So we will not be able to solve the problem. So the idea is very clear. If we train from scratch with random Gaussians, usually we never end up in getting a 3D representation which is matching the real image. So we might not be able to solve the optimization problem. It is like, so if you're training from scratch, it is like you're trying to sculpt a statue starting from scattered dust instead of clay. It is mean like, let us suppose you want to make a statue. So you are using dust for it instead of clay. So you are making use of scattered dust instead of clay. So that's the idea. And we know that with scattered dust, we will never be able to make the statue. To make the statue, we need clay. And that clay is the initialization. This clay is the initialization. And that initialization is the SfM technique, structure from motion technique. So now it's very clear that why we are using the SfM technique, because we cannot start from scratch. We cannot start training from scratch. So 3D Gaussians, we have to start with a basic structure, a basic representation, and that we will get from structure from motion, SfM technique. So the purpose of this technique is to estimate scene geometry plus camera poses before training. So the idea is that instead of random representation, we will start with a representation which will estimate scene geometry to certain extent. So using the SfM technique, our 3D Gaussians, they will like estimate a scene geometry. So they will represent a image with a scene geometry which is very close to the real image. Although the photorealistic features will be missing and many things will be missing, but the scene geometry will match a lot. And also the camera poses. So how this SfM technique works is that structure from motion technique, how it works. What we do is like the real image, this is the real image. We capture its photo from different angles, from different camera poses. From different camera poses, we capture the real photo and we feed it. So that is the input. So the input is the actual image which we want to render captured from different poses. So input will be the image along with the angle through which it was captured. The image along with the angle, image along with the angle, image along with the angle. So let us suppose 10 images I captured from different angles. Image 1 and the angle with which it was captured. Image 2, angle with which it was captured. Like that, image 10, angle with which it was captured. So that is the input. So in input, I will be having a collection of images along with the angles using which it was captured. And with this information and making use of the structure from motion technique, what output we will get is, we will get the properties of the camera, like the intrinsic and extrinsics, camera intrinsics and extrinsics, and also the sparse 3D point cloud. So two very important things we will get as the output of structure from motion. One is the camera intrinsics and extrinsics. It means like what are the internal and external properties of the camera, camera, what is its zoom, focus, brightness, contrast, all that we will be able to determine with the sample images. So uh, structure for motion technique, what it will do is that it will take a set of it will take the image captured from different angles, the same image captured from different angles as input. It will do some computation on it, and it will generate the camera intrinsics and extrinsics and also the sparse 3D point cloud. And this sparse 3D point cloud is basically the scene geometry for that image, for the real image. And a very popular tool for SfM technique is call map. Like we will not go in detail like how exactly the call map works. If you are interested, you can definitely do a research on it. It's a very popular tool. So what call map does is, like, to just get a basic idea. So call map, it estimates camera position for each image. So for each image, it will estimate the camera position, orientation of each camera. So that is the camera intrinsics and extrinsics. The camera position, the orientation of the camera, and also some more properties of the camera, and also the sparse 3D reconstruction. This is very important. Sparse 3D reconstruction is very important. So, and this sparse 3D reconstruction, this sparse 3D point cloud, this is so important that this becomes initial Gaussian centers. So these sparse points, so these sparse points will be the centers for the Gaussians. So now the idea is very clear that instead of random distribution of 3D Gaussians, now these 3D Gaussians will be centered to these points. So at least basic geometry they will satisfy. So we are starting. So this is the initialization. So we initialize the Gaussian to represent a scene geometry. And why this technique works? What's the importance of this technique? Why SfM works? Structure from motion. So see, it works because it gives correct spatial layout, because the output of SfM technique is sparse 3D point cloud. So that is like the correct spatial layout. Approximate geometry we will get, and reasonable initialization we'll get. And hence, as a result, what advantage we will get is optimization starts close to solution, faster convergence. Because of this initialization, now our optimization will not get stuck in some local minima or bad minima. Rather, it will create any noise. Optimization will converge fast, because optimization now the starting point in itself is like very close to the solution, because the basic structure we have in place. So now it's very clear that okay, 3D Gaussian splatting we have to do. We have to start with 3D Gaussians, millions of 3D Gaussians. Every 3D Gaussian will be having some random values for the parameters. So initially it will be representing some random scene. Now we cannot start training from scratch with these random 3D Gaussians. So we have to make use of the structure from motion technique. In that, what we have to do is whatever scene we want to render, the real image, what we want to render out of 3D Gaussians, that real image, we have to take the picture of it from different camera angles and feed it to the structure from motion, like a tool called call map. That is one of the way to do SfM. And call map, what it will do, it will take these inputs and it will estimate the intrinsic and extrinsics of the camera intrinsics and extrinsics, like the properties of the camera, like camera position for each image, orientation of each camera, and also the focus, brightness, and all that. And also, call map will generate this sparse 3D point cloud, which will represent the scene geometry. And then our millions of 3D Gaussians, they will be centered to these points. So they will be following a scene geometry to a certain extent. And that is the initialization, and that is the starting point of our optimization process. So the first step is the initialization.